Pleasure to have Peter kind of give us in a way, a continuation of something from almost a year ago on really multidisciplinary optimization, and I think actually extending it much further in terms of the work that you've done before. So looking forward to hearing what learnings you came out of that from the exercises that you did.
Cool. Excited to share what I worked on and talk a little bit more about MDO. So this is a presentation on multidisciplinary design optimization, and high-level plan for today. This is like kind of the conversations originating from a paper that I wrote for one of my courses. I shared it in the Slack channel, and then got invited to speak, not voluntold, but volunteered to discuss with this group. So yeah, I'm going to walk through that project / paper first, and then I guess most interesting for me and probably for the group too is to think about how the multidisciplinary optimization might actually overlap with BlockScience topics, because the project and paper itself wasn't necessarily BlockScience specific, but obviously MDO might have some applications. Originally coming up with a topic for this research project, I had some inspiration from John Seed's presentation, TSU and MDO, and then Chris has also worked on TSU and social choice, and saw there was a Slack channel and some conversation like still going today too on that, which is really cool. But I think all of these topics are like very closely related and have some overlaps, and so I thought those two topics were pretty interesting when I heard about them, and pretty much led me to deciding on MDO, just to pick something and see what happens. So I have to give a shout out. This is more of a sequel than paving new territory. But the other motivation for me is that MDO is really just a coordination tool. Its main use case at the moment is aiding decision-making between engineering teams. And of course, we have this meme about how important coordination is. We'll just be, starting with walking through a bit of the paper and the project that I worked on. A quick TLDR is that I basically spent some time like diving into MDO, just learning about the basics of what it is, what are multidisciplinary optimization problems. And then I identified a few architectures, which are basically like solution strategies for solving MDO problems. And then I found some example problems and implemented them and solved them, just to learn about MDO problems at a high level and how they're solved. And so going to just walk through a quick introduction to some MDO concepts. I'll talk about the MDO architectures in general and the ones that I focused on. And then I'll go through some of the implementation details for the solutions, and then look at some results and analysis. So this is all basically the full scope of my project. MDO stands for Multidisciplinary Design Optimization. Discipline is a key word here, discipline and disciplinary analysis. I'll quick explain what those are. There's some important variable types in the general problem formulation for MDO problems. Those are design variables, response variables, and coupled variables. So we'll take a look at those. And then finally, one of the main use cases or value propositions for MDO is related to this disciplinary coupling. So I'll just explain that briefly, and then interdisciplinary feasibility is another related topic. So this is background context for MDO. Multidisciplinary design optimization has been used mainly for solving optimization problems that span multiple disciplines. So disciplines in this case is referring to like different engineering specialties. So we can think about like traditional ones like structures or aerodynamics or fluid dynamics, things like that. And then discipline analyses, which are like models owned by those teams, examples like fluid dynamics models or finite element analysis. In our case, obviously, the models that we deal with are like CAD models, and you can think of it along the same lines, just engineering teams with specialties is like what discipline refers to. The main goal for MDO is really to improve the optimization when disciplines are coupled. But in these use cases in the real world, where there's multiple engineering teams working on the same project, there's a couple main challenges that generally arise. First is this expensive discipline analysis. So obviously, some fluid dynamic simulations or finite element analysis can be computationally intensive. Obviously, CAD models too, in our case. So that's pretty apparent. And then the second challenge is resolving disciplinary coupling. So when one engineering team's decisions affect another team's outcomes, how do you resolve that? And this is like the coordination aspect, which I think is pretty interesting. So basically a lot of the MDO architectures and solution strategies revolve around managing these two things. In the real world problem, how do you manage your expensive disciplinary analysis and resolve disciplinary coupling? And yeah, a lot of applications. Aerospace has definitely been the most prominent. Designing rockets requires a lot of engineering specialties. These are just some example images of real world use cases that I also pulled. So like in this bottom one, for example, the team designing the engine in the back of the plane is like their models and their outcomes are highly influenced by the design of the nose of the plane, actually, because all the airflow coming over the body ends up going through the engine. Obviously, highly coupled disciplines there. And now just to take a look at the variable types that we are referring to in MDO problems. The three variable types were design, response, and coupling variables. And so just to give a slow introduction to what those actually are, we'll look at a single discipline analysis case. This is not actually an MDO problem yet, technically, but it has two of the variable types, design and response. And so we have our discipline analysis, which would be some sort of simulation. And the Y vector here, this is the response variable. So that's what's produced by the disciplinary analysis. And it's sent to the optimizer to optimize some function. And the design variables are what the optimizer is optimizing over. So X is the design variables in this case. And then to look at a multiple discipline analysis example, this is where we introduce the coupling variables. And so the coupling variables are the variables that are actually shared between disciplines. So in this case, it looks like all of the response variables are also coupled variables, but in a lot of cases, there might only be one or two variables that are actually coupled. So we have the X is the design variables that are controlled by the optimizer, Y the response variables that are the output of the disciplinary analysis, and then the coupled variables are those that are shared between disciplines. So that's a quick intro on the variable types. And then finally, to look at the disciplinary coupling topic and feasibility. So disciplinary coupling happens when two or more disciplines are sharing variables, as we were looking in the multidiscipline case in the last slide. And the disciplines can obviously be highly coupled or less so, depending on how strong or how many connections they have. But the bottom line is that when there are dependencies, they need to get converged in order to find a feasible solution. So one discipline might be optimizing for their objective and come up with a value for the coupled variable that's not actually feasible for another discipline. So if they were to pass that information to the other discipline, then their model would fail or it would fall out of the constraints that they have. So those types of dependencies need to be converged. And again, this is like the main goal for MDO solution strategies or the architectures that we'll go into is to find convergence or to find a feasible solution.
Can I make a comment? This is sort of a cross stitch to some of the other subjects we've talked about, because I'm seeing here something that looks a lot like cooperative strategies for solving MAIDS, because so much of this is structural coupling in the decisions of actors within subproblems. So that graph that you're implying, which are a bunch of dependencies, it's quite literally the ways in which decisions of one actor, in this case an engineering team, affect the utilities or the objectives of another team. And so there's a framing of this that is just like popping into my head while I was looking at this. It's like there's a structural model. You could imagine modeling it as a MAID with the teams as the actors and the dependencies as the structural dependencies as what you're showing here. But as opposed to a potentially adversarial or competitive game, you can almost interpret the MDO architecture as the scheme for cooperating in solving this sort of joint utility problem where the various teams are actually not just distinct actors, but also members of a team of teams that actually has to solve the overall problem, rendering it effectively a cooperative game.
Yeah, that's interesting. I actually don't know too much about the MAIDS, so I didn't add that as a discussion topic at the end, but I know we have Octopus here, so maybe we can riff on that in the end too. But yeah, definitely coordination, cooperation game. similarities here. So converging disciplinary coupling, basically different architectures have different strategies for achieving convergence and finding a feasible solution. But ultimately, why we want to consider coupling in the end is really because interaction effects do exist in the real world, and capturing those effects lead to a better solution. So this is an example of how that works. So comparing an MDO method where the coupling is accounted for versus a sequential optimization method. I won't go into all the details of like the chart, but basically you can see MDO searches a little bit differently and ultimately ends up at a different optimal solution, where the sequential one is taking more like right angle turns because it can only optimize one discipline at a time and ends up at a different solution point. So yeah, coupling is important and exists in the real world, obviously. So in order to solve an MDO problem, you obviously have to take whatever you're dealing with in the real world and formulate it as an optimization problem. So different techniques to doing that reformulation. I think these are common across formulating any optimization problem, but some are more specific to MDO, adding variables, adding constraints, depending on your use case, and then reordering disciplines or creating sub-problems and grouping disciplines are a couple other common problem for creating a problem structure for the MDO.
Can I ask a question? Sorry, this is super fun. I love the network optimization problems. So is there a possibility that if we just look at this as a graph topology so literally there's a set of dependencies, is there a kind of way of actually optimizing I guess I'm thinking of this as a giant universe full of variables with some sort of coupling or sensitivity to each other, and then like the partitioning the problem into sub-problems becomes a matter of effectively clustering, possibly with some explicit hard constraints about what can and cannot be clustered together. But it seems like there might actually be an optimization formalization of the problem, of partitioning in the problem, so that you can then optimize it.
Yeah, definitely. So I think analyzing the coupling is a really important step to designing a problem structure that's going to help you solve the MDO problem efficiently. And I wouldn't be surprised if there's some ways to like analytically optimize that. Although I do think in real world applications, there might be some sort of like context or knowledge that you have about the problem, that almost like a feeling or maybe from experience, like these two disciplines are highly coupled, although you wouldn't necessarily believe it, and it's hard to find like quantitative.
They could be coupled indirectly. So like if the yellow node is really sensitive to the blue one, and the blue one is really sensitive to like the black one, in a way that led to a sort of net high influence of the things that aren't directly linked. But I'm also just thinking about it from the perspective of conditioning optimization problems, where whether it's a mostly intuitive or mostly analytical or even computational pre-processing, there's an aspect here where like pre-processing the problem through even a very bespoke human process, resulting in a sufficiently well-posed and well-conditioned optimization problem, will significantly improve the performance of the computational methods.
Yeah, definitely. I think that's definitely true here too. Okay, yeah, so that's creating problem structures. Obviously a lot you can do there. And then solution strategies. So how do you actually solve those problem structures? So there's different choices for picking a system level optimizer, subsystem level optimization, depending on what your structure looks like. You may or may not have sub optimization problems to run. The algorithms to resolve coupling, as we said earlier, not all problems will have coupled disciplines, but they often do. But yeah, choices on how to resolve those. And then finally, like the algorithm to handle everything above. So like, I guess even the software implementation of the problem, iterating through the different optimization sub-problems, et cetera. So all of those are different choices for solution strategies. The main takeaway here is that there are tons, like many different valid formulations for the same MDO problem. And in literature, this combination of structure and strategy is referred to as an architecture. So that's the starting point for going into MDO architectures. As MDO problems have been studied, some common architectures have emerged, and they've been organized and classified in literature and analyzed. This diagram highlights some structure of how the different architectures are organized. I drew circles around the ones that I am looking at for this project. So I started with the monolithic ones, and then I was able to get to one distributed one. Monolithic versus distributed is the main distinction in architecture type. And so monolithic is basically where you formulate a single optimization problem. And distributed is where you're formulating a system level optimization problem and subsystem level optimization problems. So naturally, the distributed architectures are maybe more complicated to implement. They might be more realistic for real world problems where you have lots of disciplines. So the architectures I looked at, there's these 3 monolithic ones and then 1 distributed one. The general MDO problem formulation, before we jump into the architectures. This is like very abstracted, but basically the goal is to minimize this objective function, and we have the design and response variables that we had covered earlier. With respect to the design variables, subject to basically it's a feasible solution for all the disciplines, all M disciplines, and then FI here represents the disciplinary analysis. So this constraint is essentially enforcing interdisciplinary feasibility. So this is quite abstracted, but it's general form for MDO problems.
Can I interject just quickly?
Yeah.
I mean, this is really nice to see because it gives you this understanding. Also, Zargham just alluded to the notion that we have like a MAIDS component here where we're thinking about that as a cooperative interaction between these different objective function subproblems. But there's also a GDS aspect here where, especially with regard to that capital X, you could even stick a subscript I onto that and say, look, the feasibility conditions, they have to have response variables and the design variables that fit for each one of the different subdisciplines across the board, such that, and then this is the nice thing about that following representation, that you have an invariant surface that you want to sit onto. And that's that capital F sub I.
Yeah.
That's essentially an invariant. And basically what you're saying is, hey, look, for all of these different choices, these things have to match up so that we actually have like a larger set. And that's very much a GDS style kind of updating procedure where you would be looking for a particular criteria that you want to like assess whether you want to throw out different types of design and responses, but that invariant surface still needs to be there for all of the things that it has to satisfy. I think that's quite a nice synergy that appears here. So
yeah, if I riff on it even further, I mean, if we introduce this X sub I, you also can imagine certain kinds of variables that are effectively in the dimension of the edges more explicitly. So you have, like, again, X here is the state of the design variables for the whole system. But insofar as we have this F of X, comma, YI, and we also have X sub, I would argue maybe sub J, so that we don't have a strict assumption about the partitioning of the problem between the design variables and the response variables. But there's a lot of, I guess, distributed optimization that has graph structure. I mean, without overly plugging my own dissertation, like I spent most of my dissertation chasing problems which have underlying network structure. And once you integrate some of the GDS stuff, which allows for dynamics and characterization of constraints or objectives in terms of invariance, I think there's some really interesting ways in which this problem could be distributed more widely, or just computed more efficiently if you have an explicit encoding of the network structure, and you can take advantage of that network structure to avoid, say, invoking expensive sub-optimization problems more often than you need to.
Yes, I wanted to comment on that, actually. This is pretty cool, Peter. So in my world, I would call this bi-level optimization problem, right? You have a core objective, you have a set X of your first level. Sometimes we call it like the leader and the follower. So the leader is the upper level, right, optimization problem. And then you have the FI of XY, which is the follower in this case, right? This is the inner optimization problem that happens to be part of your constraint set. And something that I actually was going to ask is, this is pretty cool and actually it's pretty useful across so many applications, but it comes with the difficulty that it's, again, a bi-level optimization problem, which is sometimes pretty often very hard to solve. And so I'm just wondering if, Zargham just mentioned, of course, if we have a network structure that is friendly and that has some nice structure that we can take advantage of and solve easily, then that may make things easier. Actually, my second paper, I actually had a bi-level optimization problem similar to this one. And that's why I'm telling you it was pretty hard to solve. So I'm just wondering, these disciplines, and I see that you guys were talking with NASA about these type of problems. Like, I'm just even wondering how they are trying to solve these type of problems to the scale that it's needed.
On the NASA side, so we were talking with some folks from the MBEE team, the model-based engineering environment team, a bit about how you keep track of and access, like basically how you, almost like COI-like stuff, knowledge organization infrastructure around models and functions and their maintenance, mutation safety and stuff. But we talked a little bit about MDO because there's a project that Drumsheet had presented on last year, which has some overlaps within their team structure. Because at NASA, we're talking to the people basically doing open source software build for model-based systems engineering. And even though the conversation started from a COI MBEE perspective, yeah, we like touched on MDO a little bit, and they had actually just expressed that they would have brought some other people if we wanted to talk about that, which sounds like it's the case here too, right? If we would have gone into that with a less COI focused discussion, we probably would have invited Peter, and it sounds like it would have made sense to invite you. So keep an eye on where those conversations go. They're currently in the shape of, we made some friends because they do MBSE and open source software stuff. And I mean, we do MBSE and open source software stuff, albeit with a slightly different focus. So that's the answer from the, like, yes, we were in fact talking to people at NASA about this, but at a level of like knowledge sharing and learning.
Yeah, I would say that's an interesting point about the network structures. And then in terms of solving these in the real world, that was one of the learnings that I was going to get to too. Like, the knowledge of the real world problem is essential in order to be able to formulate and solve a problem. The value proposition for MDO is in the real world, where you have these like crazy large disciplinary analysis models that are highly coupled. So you really do need like a real world problem to be able to apply these things to like see the value.
My intuition is that this is actually very actionable even on some relatively simple problems as soon as they cross the threshold into more than one subsystem. And I'll give you the example from the DeSci report that we've been writing up. Like, my design space, as I articulated it within the report, is 3 subsystems. One is a microeconomic model that relates to the day-to-day utility, so how it's used, the token access gates, specific activities, and it's very much defined at a micro level. There's a macro level one, which has constraints related to supply and circulation. And there's a subsidy programs type submodel that relates to how like rewards from a pool of available funds are then deployed to drive specific objectives within the system. And that's actually arguably the basis for an MDO problem. And although I don't think we're going to be going into a simulation phase on that project, because they need to like take that architecture, quite literally, that's structure and strategy, and run with it. But if they were coming back to us and saying, hey, we need to build a simulation, it actually probably makes sense to build 3 independent simulators that focus on their discipline for the subproblem. And then insofar as we know that they're coupled, like they are coupled, we would want to take a tactic like this, and that's a 3 subsystem problem. So I see this as very natural. And I guess to round it out to the points about conditioning and network structure earlier, like if you start with the conceptual model and then the subproblems, and then the ability to design optimizers or at least simulations of the subproblems, and then you start worrying about coupling them, it's in the question of how to couple them that we also need to deal with things like conditioning. And that might mean that the dependencies are directed and we want to look carefully at them. It may also lead to rescaling variables or creating normalized representations. And I think there's a lot of interesting, again, needs to be done by people with some domain expertise, but a lot of interesting opportunities to create sub-models and coordinate amongst them rather than trying to unify some of these like big gnarly models that operate at different scales or on different phenomena.
Okay, cool. Yep. So there was 4 architectures that I looked at. 3 of them were monolithic. 1 was distributed. So I'm just going to go through, quickly cover some of the differences just to get an idea of how these architectures can be designed differently. So the first is called the all-at-once AAO method. It's very general, basically has overkill in terms of constraints, variables, and control of the optimizer. They're copied everywhere. There's extra constraints and everything, but it's the most general MDO architecture, and it's formulated as a single optimization problem. So basically, we have one new variable change from the general formulation that we were just looking at. It's this YT. So these are coupled variable targets, basically copies of a coupled response variable. The copy is used in a discipline other than where it was generated as a response. So there's creating the copies is one change, and then another change is because we have the copies of the coupled variables, we need to add these consistency constraints. So that is this row here, these constraints here, just to enforce that the copies remain equal to the original response variable. And then also in this architecture is this discipline residual. And so the residuals here are set, the constraint set equal to 0, basically to ensure that the solution is feasible for all disciplines. So yeah, residuals for disciplines 1 through M. And yeah, so as I was saying, it's kind of overkill. It includes like all of the copied variables, all of the residuals, everything.
I throw a quick flag out there. The making the residuals explicit like this with the R sub I and equals 0 is a nice way to make the solution like more legible, because it means there'll be Lagrange multipliers explicitly for each of the disciplines. So when you go to solve this, right, the Lagrange multiplier associated with each of the constraints script R sub I will tell you something about how much maybe you might need to relax the constraints, or just from like a meta perspective, it's actually really important that those are broken out so that they each get their own multipliers.
Yeah, okay. Cool. And then moving on to simultaneous analysis and design. One small change from the AAO architecture is that we removed the coupled variable targets and the consistency constraints, since there's no longer coupled. But because we're still optimizing everything all at once, we're still able to reach interdisciplinary feasibility with the same residual constraints. It's just a slightly smaller problem size. So it's a pretty easy step to the SAND architecture from the AAO. And then, so now this is where it gets a little bit more interesting. So this is called the individual disciplinary feasible method. In this architecture, the residual functions are removed, and we actually get to use the disciplinary analysis for each discipline. We can see in this diagram here, we have like actual information flowing now. It's not just a single problem statement, and we have information flowing from the disciplinary analysis to the optimizer and back to the disciplinary analysis. There are benefits to the residuals, but it's not always possible to calculate the residuals. So cases like that, we would need an architecture that doesn't require them.
I would argue they're not necessarily gone. I think that you just, now they live in the disciplinary analysis. So this doesn't describe how the disciplinary analysis works, but if you were to like reason about it post hoc, like once you've run it, you should at the very least be able to extract something about the trace of the local problem to tell you something about how it got to feasibility. And one interesting thought about this is that the macro optimizer basically is enforcing this sort of, or is not the one enforcing feasibility at the disciplinary level, but again, that presumably is happening within the disciplinary analysis. So this is, I would argue, now already starting to be a properly distributed architecture, and you're not just distributing the computation, you're distributing the responsibility for satisfying the constraints.
Yep, okay, interesting, yeah. And so then this architecture is able to run in parallel, or the discipline analysis are able to run in parallel for this architecture since we're splitting them out. And then I just underlined here, enforcing the consistency constraints are what enforce the feasible solution for the disciplines, although, yeah. And
well, then, I want to clarify what I was saying. So, because I'm hoping this is helpful, that Y assertion is really, from my understanding, it's telling me that the yi super t, so the y sub I in the macro optimizer is the yi that came from the disciplinary analysis I. So that's like a binding. It's a thing that says, hey, we don't get to change this. This came from here. And so it's a way of connecting all of the individual disciplinary analysis response variables to the response variable that is in the macro optimizer. But insofar as that response was generated by a process on the disciplinary analysis side that was feasible is essentially, from the perspective of that disciplinary analysis, is the burden of the disciplinary analysis itself, the thing that pretty Y super I. And so what you're doing here in this individual disciplinary feasibility is doing what is effectively a hub and spoke type model. You have like an orchestrator or coordinator in the optimizer, the thing labeled optimizer here, and then you have a bunch of sub problems, and it's basically just saying, do an iteration of the macro problem, then send copies of everything out to everyone, let them do their things in parallel, collect up their results, retrieve the results, and do another iteration of the parent optimizer. Mm-hmm. And you can think of that as a sort of hub and spoke model, right? Where it's just, I do my thing, I tell everybody, they do their thing, and then they send me back their results and I do my thing. And my intuition here is that we're moving into something a little less centrally managed, but still ultimately solving a central optimization problem. So it's incremental. Yeah. You're growing from the kitchen sink style, like canonical form, hey, solve this by throwing all the computation at it, to something a little bit more specialized, to something parallelizable, to something that is like arguably distributed in a more flexible way.
Mm-hmm. Yeah, and this is like the furthest it gets basically on the monolithic architectures before it gets even more distributed. So, so that makes sense. And then the final architecture that I looked at, which is actually the first distributed architecture by those classifications earlier. So we have our system level optimizer and sub-problem optimizer. So I guess the main difference between this and the individual disciplinary feasible method is that these discipline analyses aren't necessarily their own optimization problems. So in this architecture, these are sub-optimization problems where the objectives are actually where the interdisciplinary feasibility is enforced. So this architecture is reorganizing all of the disciplines in the problem into different subproblems. You can group multiple disciplines into a subproblem, and the subproblems are responsible for optimizing the variables that are local to that problem.
So then that makes some sense. I think then what I'm seeing that I missed on the first pass is just actually being really specific about effectively the observability and controllability in the design problem itself. So like when you run a disciplinary analysis and produce a response variable, you're essentially making observations about the consequence of a set of design decisions. So both the decision variables or the design variables, which are effectively your controllable parameters across the whole thing, and then your observable variables are effectively the response variables. And so this basically becomes a kind of distributed controls problem where you are potentially locally in this last one, but more centrally in the previous one, making decisions about the design variables X, and then you're observing the consequences of the changes to the design variable X on the various response variables Y, but that the observability is a consequence of the disciplinary analysis, but the controllability is a consequence of where the actual decision variables are. And then this brings us back to this as a network problem in this last case, where you can effectively localize the various decision variables and response variables, and the coupling can be weird. Like you could have places where if there's a network structure, the decision variable in subsystem I actually has most of its consequences on the response variables in subsystem J. And that's how you would start to use something like a controllability and observability matrix. Again, I'm pushing in an optimization as controls vernacular here, but like actually the network structure and partitioning the problem might come from, at least for a big problem, understanding what is coupled to what, not just explicitly, but in terms of like input output, like response. Like if there's high sensitivity of this this response variable to this state variable, then we have high coupling. If there's that high sensitivity, even if they're not in the same partition or in the same disciplinary analysis.
Okay. Yeah. Is that all analysis that would happen as like conditioning for the problems like we were talking about? Like that's all?
Yeah, I think so. I'm thinking about how to set the problems up. And I guess I'm coming at this from a perspective where I spent most of my dissertation work on distributed optimization. So like I'm making assumptions maybe that are, whether they're right or wrong, they're baked deep in. But it seems to me that there's like a lot of power here But to your point earlier, actually the devil is going to be in the details at the level of the domain-specific analysis, understanding the systems engineering problem as well as the subsystems and the way they couple. But part of the reason I like this so much is that it puts a little bit more formalism around the systems engineer's job, because their job isn't to develop the disciplinary model. Their job is to figure out how to synthesize and satisfy all of the disciplinary subproblems such a way that the overall system can reasonably be expected to satisfy like work as a whole. And that often gets fuzzy, right? Like the subproblems can get really rigorous, and here's my model and here's my optimization, and everyone's arguing for the objectivity of their results or whatever. But then when you try to put it back together, it's still human-y. You're like, but like this conflicts with that. Like you can't do that. And like you have this integration process of the models of the design that can get messy and kind of returns to a very subjective human conversation-y level. I'm not saying that's bad. We've got to keep some of that. But what this does is it pulls it into this problem specification, factoring, structuring, conditioning, so that you have a way of integrating various models together where all you need to know about them is what their decision variables like X are and what their response variables Y are. And then you can have the factoring out of the constraints across the problem so that these things don't need to be as tightly. And again, I'm a little biased towards this more collaborative optimization architecture because it matches up to some of my experience with distributed optimization. It's very likely that in any real applications that we would surface, they'd probably end up looking more like the first or second one, because I think we'd end up with 2 to 3 disciplines, and the underlying challenge would be mostly around getting those systems to conform enough to talk to each other. Like if I have a micro model and a macro model, they literally run on different timescales. And so you're like, okay, that means if I want to optimize them together, I need a way of meaningfully interpreting the micro level model's behavior given a set of macro model expected dynamics and vice versa. And that's ultimately going to be the description of the coupling between the decision and response variables. And so most of it is actually going to be formulating this MDO. And then in some cases, we might not even need to run MDO. It might be that formulating the MDO is just the way to give an explicit and analytical description of the relationships between 2 or 3 models. And then if we end up doing an independent human orchestrated version of an MDO process, we might still get better answers than if we hadn't started by formulating the MDO.
Okay. Yeah, that's really interesting. I did read some articles about MDO. Some people just find the main use case for MDO be to like formulate the problem and not necessarily use the architecture for running the optimization problem to find a solution.
To be clear, I just think it's the table stakes, right? You can't do the second part. Just think of it from a path dependence perspective. If you can't reliably formulate MDO problems, then you can't run them. But also, if you can't formulate them, you can't condition them. So there's a way that I think you have to go from formulating in the abstract sense, just as a set of relationships and understanding the couplings and whatnot, and documenting it. And if you can do that, then you can do things like possibly more analytic assessments of whether it's a well-conditioned problem, because given the computational intensity, I would hesitate to just throw a problem at this. You would want to spend a little bit of time to the best of your ability to structure and condition it, and then you're basically running a kind of orchestration level process, which then runs a bunch of other processes. And since that's going to be resource intensive and expensive, you want to make sure that you have a well-conditioned problem and that you can do it manually as a bunch of sub-problems and look at how they relate to each other before you would commit the resources to run the actual MDO optimization. And for us as BlockScience, I would say the first step is I'd like to see us adopt some MDO type formulation for problems that are sort of multi-scale or multidisciplinary in the sense that they invoke models that don't operate on the same time scale, but are nonetheless interacting through some of their variables, which we do have frequently. And then we can worry about questions of conditioning and computational complexity and whether or not we want to use an MDO strategy for actually running a let's say a PSUU over a system that contains, and again, the simple case here is a micro model, a macro model. And if that works, then we could figure out how to make that more scalable and more reliable. But we really don't need to jump to there. We just need to actually express that problem as an MDO problem and think about how well or not it's conditioned.
Yeah.
In the time that we've got left, maybe Peter, do you want to just go through quickly what you got from your horse race? Just looking at maybe one of the two problems. I know we only have 5 minutes, but I think it's nice just to focus on one of the ones you think is the best and give us a quick lowdown. Thanks.
Yeah, I was actually going to breeze through this part anyways. So the implementation of some of the example problems. So there were 2 example problems that I looked at. One was just a geometric programming problem. The other was some propane combustion problem. And I basically reformulated. So this is the geometric programming problem, and these slides are showing how the original problem is reformulated into an MDO problem. So first taking this and defining disciplines, assigning constraints, categorizing variables, and then from the changes that I made on the previous slide, these are some of the additional steps to reformulate it into the AAO architecture. And here reformulating it into the SAND architecture. So some of that stuff is pretty straightforward. I'll just jump to the propane combustion problem too, because I did the collaborative optimization architecture for that problem. So yeah, so for the propane combustion problem, starting with the AAO formulation, like making a bunch of changes in order to reformulate it into the collaborative optimization architecture, the CO, the last one we were looking at on the paper. So here defining the subproblems, and of course I'm like the one assigning the disciplines to these subproblems. It's a generic example problem. I don't have any context on how those disciplines may or may not be coupled, but I just picked it and assigned them and then formulated the problem. And then in terms of implementing and solving them, all the 3 monolithic architectures get implemented and solved using any optimizer. I think I used SciPy, but the collaborative optimization architecture, as we noticed, there's actual like subproblems that need to run. So the way that I implemented that was basically just within the constraints of the system level optimization problem, embedding another optimizer to run. So that was a formulation and implementation. As for the analysis, the data that came out of it was, I would say, as expected. There were 2 metrics that I looked at. One was solution accuracy, and the other was the disciplinary function calls. So this is one of like the key performance factors for solving an MDO problem, is how many times do you have to go back and query the discipline analysis, because that's the expensive part. And for these example problems, the monolithic architectures had a lot fewer function calls than the distributed one. AAO was the largest problem, so it took the most function calls. SAND was actually the most efficient. Basically, the conclusions of the project were that the performance was as expected, given the problem structures. So nothing like too crazy or interesting on like the implementation and data analysis side of it. But I think my main takeaway is that there's a lot of pre-work, as we were just talking about. There's a lot of work that goes into formulating the problem before any of the implementation happens, and understanding how problems are coupled, what is the context of your real world problem that is important for producing a good solution in the end. That, from this experience, takes a lot more time and is way more important than the last few steps of implementation and solving. So,
did you get a feeling for whether or not open MDAO is a way to go in terms of helping that sort of pre-filtering step, or is that coming later in the process?
I would say it's later in the process. So it's after you've formulated and you've designed your problem with an architecture, then you use OpenMDO to implement. It definitely helps, especially with gradient-based optimization. It's like incredibly useful, but that's a later step. Yeah. So these were just some of the discussion topics that I thought would be interesting to basically dive into related to MDO, and some things that are more relevant to BlockScience, like PSU, OpenMDAO with CAD, the social choice, multi-objective optimization. I'd have a slide on each of these topics. It would be awesome to talk through them at some point. I'm obviously also very interested to see how this could be useful for BlockScience, actually applying it to a real world use case, because I think that's where the value proposition, again, of multidisciplinary optimization is in the real world, like coordinating teams with expensive disciplinary analysis and highly coupled disciplines. So this research was great for getting an intuition about the architectures and the problem design, but would be really awesome to see how some of this looks in the real world.
Well, great. Yeah, well, thanks,
Cool.
Peter. That was super cool and really interesting. Thanks.
For sure. Thanks for coming, everyone.